Okay, 2018 Leaving Cert Tired of a question 4, paper 1 was the proof of DeMoivre's theorem. Prove using induction that if n is a positive integer, then cos theta plus I sine theta to the power of n is equal to cos n theta plus I sine n theta. So we have to show it's true for n is equal to 1. Then we assume true for n is equal to k. And then we prove true for n is equal to k plus 1. So let's have a look here. Cos theta, when n is equal to 1, is the cos of theta plus I sine theta to the power of 1. Is that equal to the cos of 1 theta plus I sine 1 theta? Of course it is. So we just write cos theta plus I sine theta equals cos theta plus I sine theta. We assume true for n is equal to k. So we get the cos of theta plus I sine theta to the power of k, and we always use this assumption in the k plus 1 is equal to the cos of k theta plus I sine k theta. And then we show true for n is equal to k plus 1. So that's going to give us the cos of theta plus I sine theta to the power of k plus 1 equals the cos of k plus 1 times theta plus I sine k plus 1 times theta. So if we separate out this guy into cos theta plus I sine theta to the power of k times cos theta plus I sine theta to the power of 1, and then simplify it down, we can use my assumption to replace this guy, cos theta plus I sine theta to the power of k, with this one, because that's what we've assumed true. So if we bring that one down, cos k theta plus I sine k theta by the cos of theta plus I times the sine of theta to the power of 1, and then multiply this out, we should get the right hand side. Let's multiply this out. We get the cos of k theta multiplied by the cos of theta plus the cos of k theta multiplied by I times the sine of theta plus I times the sine of k theta by cos theta, and then we have plus I squared, which is going to give us minus 1. You could change this to a minus 1 straight away if you wanted, and that's going to be by the sine of k theta by the sine of theta. So if we bring the two real parts together, this is going to be a minus 1, so that's one of the real parts and this is one of the real parts. So we're going to get cos k theta cos theta minus sine k theta sine theta sine k theta sine theta, and then we're going to have plus I times these two added together. So the first one is cos k theta sine theta, and the second one is plus sine k theta cos theta. So this will give us two trigonometric identities. First one being cos A cos B minus sine A sine B, and the second one is going to be in a slightly different order. It's going to be sine A cos B, sine A cos B, just the way it's written in the formula booklet, sine A cos B plus cos A sine B. And if we write down underneath what these two things are equal to, cos A cos B minus sine A sine B is the cos of A plus B, and sine A cos B plus cos A sine B is the sine of A plus B. And you can see now this is going to give us theta plus k theta, which is what this will be here. So let's have a look if we simplify that down. this is going to then give me. Therefore, we can say that the first one plus the second one is going to be the cos of a plus b, which is the cos of a k theta plus b, which is theta, two angles. So this simplifies down quite easily, plus I times the sine of a plus b, which is the sine of k theta plus theta. And if we factorize theta out of these, we're going to get the cos of theta by k plus 1 plus I times the sine of theta by k plus 1, which you can see is equal to this guy here. Therefore, we've got our proof. Therefore, shown true for n equals to 1, assumed true for n equal to k, proven true for n is equal to k plus 1, therefore true for all values of k. And that's DeMoivre's proof by induction. Part B in this question asks us to hence or otherwise find minus a half plus root 3 over 2i to the power of 3 in its simplest form. So we could multiply out the 3 brackets, but let's do it using complex numbers, where we know the complex numbers are cos theta plus I sine theta, every single one of them. So where is cos negative and sine positive? See, cos is only positive down there. We're looking for cos negative. So cos is negative in here. It's also negative in here. But in this one, sine is negative as well. So we can see here, sine is positive in this one. So this is the sector we're going to use. We know that the cos of 60 is equal to 1 over 2, or if you don't, you should know. And the sine of 60 is equal to root 3 over 2. So 60 is the angle we're going to help us get into this question. So let's draw my 60-degree angle in here. There's my 60. So what angle am I dealing with here? I'm dealing with 120. So 120 is the angle in this question that we're going to use. So that's 2 times 60, 2 times pi over 3. So we can say that this complex number becomes the cos of 2 pi over 3 plus I times the sine of 2 pi over 3 to the power of 3. And we know from previous, where's that 3 going to go? It's going to multiply by the modulus, or it's going to go to the power of the modulus. Well, the modulus in this case is just 1. We can see this 1 here, we don't need it. So it's just going to be the cos of 3 times 2 pi over 3 plus I times the sine of 3 times 2 pi over 3. So we just need to work this out. 3 times 120 is, if we write it in degree form, 360 plus I times the sine of 360. So it's this point here on the unit circle, which is 1, 0. So that means that the cos of 360 and the cos of 0, we go all the way around, we can see the cos is going to be 1 and the sine is going to be 0 based on our knowledge of the unit circle and the points on the unit circle. So this is going to give me a 1, this is going to give me a 0i, and that's that complex number written in its simplest form.